In the previous video, we have implemented LSystem class, so we can now generate the output from our rules and from our axiom. Now, what we need to do is to try visualizing the output of our LSystem to see the possibilities that we have to implement this LSystem into a procedural generation algorithm for creating a town. First, we will create a helper class. We will call it agent parameters. So let's create a new C# script and let's call it agent parameters. Let's open it up. Okay, let's delete everything that we have inside our class and let's delete the monobehavior inheritance. This will be a simple C# class, and as I have told you before, when we are saving and loading the position of our agent, when we are moving it around to draw our output, we need to save its position and rotation. So to do that, we are going to implement this helper class. Inside it, we are going to have three variables. First one will be a vector3 position, so let's type public vector3 position. Next, we will need also a direction. So we are going to know where do we want to go in which direction as a vector. And we are going to add this vector to the position to move the agent. And lastly, we also will want to save the length. So public int length. Now, as we have discussed previously, there was a piece of information in our theory that we want to vary the length that we use to move the agent. So we are not going to use one unit by which we move our agent, but we are going to calculate the length so the town gets smaller the farther we get. It will be more clear in a minute when we start drawing. So let's save it, let's go back to Unity, and we will want to create a new C# class called simple visualizer. Click create C# script and let's call it simple visualizer. And let's open it up. Okay, so let's delete everything from this class that was pre-generated for us. I'm going to change the name to be correct. So this class will be responsible for drawing our visualization of what we have outputted from our LSystem generator. So first of all, we need to have a reference to our LSystem. So let's type LSystem generator. Let's call it LSystem. We will want to visualize the points that our agent has reached and also the path that it has traveled. So for points, we are going to create a list of vector3s. I need to be using system collections generic for this. Let's type vector3 and let's call it position. Positions equals a new list. So we are going to save inside this list the positions that our agent has traveled to. Next, we are going to create a public game object prefab, and we will place this prefab in places where our agent has visited. Next, we need a material, so let's call public material. Let's call it line material, because we are going to use a line renderer class from Unity to draw a line instead of showing the path as prefabs. So we are going to visualize our paths using lines for now. And to draw this, we need two more parameters. I have mentioned already the length that we will modify. So let's type private int length. So for the beginning, we will set the length to be 8. And let's type private float angle equals 90. So this will be the angle that our agent will use to turn left or right. And basically, we would modify both of those parameters to achieve a little bit different results every time we generate something. And we need to use our angle equals 90 degrees because we have our tiles as road. So we only have the option to use angle 90 degrees to show the road. For now, let's use this length and let's right click on it, quick actions, and let's encapsulate field and use property. This will create us this getter for length, and we will need to modify it a bit, because to be honest, I didn't put a lot of thought about how to calculate this length. This is one place that you can improve upon, but basically what I have established is that we need to have a minimal length of 1 despite the number of generations that we have created. So we need the simple check for length. If length is greater than 0, we are going to simply return the length field that we have implemented previously, so our 8. But else, we need to ensure that our length is at least 1 for our points to be visible on our map, on our ground. So this is something that I have came up with just to ensure we do not run out of length, because we are going to reduce the length by 1 or by 2 the further we go. Okay, with this digression to the implementation of this method, we need to have a way to visualize our sequence. So let's create private void visualize sequence method. And we are going to pass into visualize sequence our string sequence. So sequence is the output of our L system. So to use this method, we are going to create start, and we are going to call here var sequence equals our L system generate our sentence, and we are going to call visualize sequence and pass this sequence to our method. So now all that remains is to implement this visualize sequence method. Now before we can visualize our sequence, we need to have a way to map this sequence, so the sequence of characters, to concrete commands for our agent. So we are going to create a public enum, and I have called it encoding letters. And what I want to have here is unknown. So this will be the default command. We will have save. And according to the table that I have previously shown you, it will be in square brackets, the starting square brackets. Next, we are going to say load, and this will be the ending square bracket. Next, what we need is also to draw, and this will be letter F. We have also turn right. This will be symbol plus, and at the end we are going to have turn left, and this will be equal to minus symbol. Okay, in the original implementation we also have a move symbol, which was a line, but we are not using this because we have an output that is the whole line appended. So we have the whole line of input from our L system, and we can just draw this line by line. So having implemented the mapping, we can now implement this visualize sequence method. In here, what we need to do is first to implement a collection that will gather the saved agent parameters when we save and load the agent position. For this, we are going to use a stack. So stack is type of collection that provides us with functionality that last in element will be the first out. So we will save the last point, because that's basically how our system will work. We are going to go save the point, go up, save the point, go to the right, for example, and then what we want to load is the second save point. That's why we need a last in, first out LIFO structure, and stack will provide us with that functionality. So it will be a stack of agent parameters, so our custom class. We will call it save points equals new stack. Okay, now we can save and load our points for our agent. Next, what we need to do is have a var current position, and we will set it to be vector 3.0. you could use the game object's position for this parameter and say that you place multiple simple visualizer around the map, and in those places the town will be generated. Next, what we need to save is vector3 direction vector3 dot forward, which will be the z-axis. So this is the starting direction, and we also need a vector3 temp position vector3.0. Okay, great. And this will be used when we are drawing our road. We will set the temp position to current position, we will calculate the end position, and we will draw a line from temp position to the next position, which will be the current position. It will be much clearer when we implement this in the code. So at last, we need to add our current position to our positions. So add our current position. So this positions was our array that we will use to draw the prefabs in places that our agent has stopped or started from. So now what we need to do is go for each var letter in our sequence. So this is similar to what we have done in our else system, and that's why other else systems can draw and iterate at the same time. But since we have split it, we need to loop for each letter again. And what we will need to do here is create an encoding letter, encoding equals encoding letter. So what does it mean? Well, we have our encoding. So we need to ensure that each letter in our sequence, so what our else system returns, is mapped inside this enum. So it only can be 1 square brackets f plus and minus. And if such letters are present here in the sequence, we can map those letters as the encoding. And now the great part about this is we can use switch statement, and we can type encoding, and if we use arrow down, it will automatically create for us different cases, different scenarios, what it can be, and this is much clearer what we want the agent to do, because now we know that the case is save, load, draw. Let's change this name. Okay, turn right, turn left. We can delete the first case because it will never be this. And next, what we need to do is implement each of those points. So starting from save behavior, what we need to do is to add to our save points, which is our stack. We are going to call push, and what we need to push is our new agent parameter, and here we can pass our position is equal to current position, so we are saving the position of our agent. Direction equals direction, so we have saved the direction that we want to restore upon reloading this agent parameters, and length will be our current length. But instead of the field, we want to use property length. Okay, and break. Great. Next, if we see the load symbol, so if our save points count is greater than 0, because there might be an error in our sequence, we will restore this. So var agent parameter equals our save points dot pop. So it will get us our last saved position, and we are going to say current position equals agent parameter dot position. Next, direction equals agent parameter dot direction, and we will reload the length equals agent parameter dot length. So this is how we load our saved position for our agent. But what happens is if the count is less or equal to 0, so else we will throw a new system.exception, and let's say don't have saved point in our stack. Okay, and that basically will throw us an error, so we know what is the issue in our code. Okay, next what we need to do is to say temp position in our draw equals current position. So as I have told you before, we need to save it to draw a line. We will say current position plus equals direction, so which way we want to go, times our length. So this will give us a new point that is moved by the length in the direction that we have. And what we would need to call is a function called drawAlign. So let's call drawLine. And we are going to pass here temp position. We are going to pass here current position and a color .red. Okay, and let's Alt Enter on this and generate this method. We need to implement it by ourselves. Let's slide down and search for this. Here it is. And what we need to create here is a game object line equals new game object. Let's call it line. Next, line transform position, and we will say that this is equal. So this temp position is starting point. So let's rename it to start, and this will be the end. So the next position. What we need to create is set the line transform to be at the start. Next, we will add to our line, add component, and we will use our line renderer, which I have told you before. We are going to use the Unity's line renderer that is able to render a line between 2 points. And one last thing we need to do is call var line renderer equals add component, because it returns us this object. Now we have the reference to this line renderer. We will call line renderer, and we can copy this name dot material, and we will set it to our line material that we have provided as the input argument for our mono behavior. Next, line renderer dot start color equals color. It will be we need to rename it to color because it doesn't have to be red. Next, our line end color equals color. What else? Line start width equals 0.1 f, and line render end width, it will be 0.1 f. Great. And line set position 0 start and line render set position 1 end. So this sets our line to be drawn between start point, so 0 point is the starting point of our line, and point number 1 is the end point for our line. So this will draw us a line between those 2 points that we have established. Okay, let's slide up to where we have finished. We have finished drawing the line, and what we need to do it here as well, we are going to say length minus equals 2, which will cause our next line to be shorter. And this means that when we start drawing, we are going upwards. The line length is 8, but when we turn right, the line length will be only 6, then 4, then 2, and as you can see, there was an issue where we could end up with length of 0, and that's why this is the field where you can upgrade the design of this. But anyways, we have drawn a line, and what we need to do now is positions, add, because this was our array, and we are going to add our current position. And last 2 cases is turning. So turning will be simple direction equals, we are going to use quaternion, and to calculate a new angle, we are going to call a function called angle axis, which will create us a rotation, which rotates angle degrees around axis. So this is perfect because we can provide this angle that we have created, and turning right means we add to the angle, so the angle is positive, and we need to provide the vector up. So vector 3 up is the y-axis, so a y-axis goes straight forward up, and we are drawing our streets on x and z plane. So that's why a vector 3 up is upwards direction. And to add to our current direction, we are going to multiply it by direction. And this will return us a new vector that represents our angle turned to the right. And we can copy this statement, because for turn left, we only need to add minus before an angle, and it will rotate our direction vector to the left or minus 90 degrees, whatever the basic direction is of our direction vector. But there is one more thing that we need to do. We want to spawn points where our agent has visited. So for each position in our positions array that we have added our points to, we are going to say instantiate. We are going to say our prefab, our position, and set quaternion.identity as rotation. Okay, great. So this is our whole class. One issue that I have is that the name is correct, but the name of our script is incorrect. So let's go back to Unity. Okay, I need to rename this to have the correct name as the same as the class have. And what we need to do now is to make sure our rule contains the symbol that we have allowed in our mapping. So what should we put here? We are going to use one of the reference from the book, so one of the rules from the book, and as the rule output we will put the sequence that I have shown you in the theoretical section. So plus f minus f, and between saving both of those points. And we also need to change the else system root sentence. So the root sentence for our example was open square brackets f inside minus minus f. But we have not yet created our visualizer game object, so let's click in the hierarchy, right click, create new game object. We're going to call it simple visualizer. And we are going to drag our script simple visualizer into this game object. Next, we need to drag our else system into the field else system. We need a prefab, so in prefabs folder, let's choose our sphere, let's drag it into the prefab field, and we need to have a line material because we are going to render a line. So let's go to materials, and we have our line material. Now we can press play, and you should see something like this. We can increase the light, so let's go to direct light, and we can choose intensity, set it to 2, and this is much lighter now. So you should see something like this. We are going to discuss this creation and how to tweak it in the next video.